Welcome back. Last time we were solving exponential equations, right? So we were at alpha 59, and we did majority of the questions. And I think we have the last group to cover, didn't we? Yeah, 14. We did up to 14. Okay, we did up to 14. And we have learned these properties, right? Definition and properties. And we're going to, these are, one is a definition and the other one is what we have derived from that definition. So moving forward, we did number 14. So let's look at how we will do number 15 and 16 as a warm up. Okay, solving for x. Suppose we have 5 to the power of x equals to 13, right? Now this time you don't have a perfect power waiting for us. So what do? We can use definition. Right? We can use definition. In the case of number 15, apply definition, which is right here, right? Apply the definition. Okay, I think by this time you guys probably is very good at applying the definition already. And the base is 5, so we have a 5 to the power of x, right? To the power of x. So this is x. The base is 5. Omega is 13. So omega is 13. Right? So omega is 13. So there you go. You get your solution already. We get our solution, which is log base 5 of 13. Did I record? No, I did. Good morning. Okay. Good morning, Marcelo. Thank you. Okay. So that's how we did number 15. And that's how we did number 15. For number 16, okay, over time, you don't have to go through this process anymore. And you guys just get there. And the other technique people call it is taking logarithm on both sides. Okay, we're not gonna, we're gonna address that later. Okay, so x equals to ln 3. So that's the solution. Okay. Then you say, how do I know this if the solution is right? Right? How do I know if the solution is right? We can always check. Okay. How do we check? When we go back to one side of the equation, for example, we go back to the equation on the left-hand side, right? Which is 5 to the power of x. And now we found a solution for x, which is log base 5 of 13. Right, we replace x by it. And what does this equal to? Of course, this equals to 13, right? Did you guys see the quizzes I give you? Okay. So this is the moment we get to apply this property. That property, right? So we get to apply that property. And for this latter one, x equals √3, how do I know that is the solution? You can also check. Right? And check on the left-hand side. Right? It's e to the power x. And now we found x is ln 3. So replace x by ln 3. And you apply the same property here is just going to be equals to 3, which is the right hand side. Therefore, these are solutions. So we know how to find solutions in those cases of 51, 59A. And if you need more exercise, you can go to 59B. Okay. But today we want to work on 60A. We want to work on 60A. 60A is called alpha 60A. Are you guys ready? Are you guys ready? So alpha 60A. Okay, it's still solving for X. So all of these are if statement. Solve for X. Okay, and you're told using the definition of logarithm. Logarithm. Okay, take the first one for example. Okay, we have a log base 2 of X equals to 5. And we want to know what X would be. Right? So once again, our definition would be very useful. We'll see if the other property was, will be useful, but we bring them along. We'll bring them along. Right? So this is the property we're going to get to use. How do we use it? Right? How do we use it? Right? Let's see how we apply the property, how we apply the definition. We have a base 2 here, so the base is 2. So base is 2. Everywhere base is 2. Omega. What is omega? What is the quantity at the place of omega? Log base 2, so this is X. Right? This is X. And at the place of omega. Right? Triangle is 5. So triangle is 5. See, and the base is for sure satisfying that condition, and we're good. So right here, you can see from the definition, you can directly get 2 to the power of what? 5, 2 to the power of 5. 2 to the power of 5, of course, is 32. Okay, so that's how we apply definition. Do you need to show this piece? No, you don't need to show that. You can, to solve this equation, you just have to go just one step. It's really just one step. Do you guys want to try it? Okay, how about you guys try number 3? You guys try number 3. Okay, your turn. Number 3. Log base 5 of X equals to 4. Solve for X. What will be the X? What will be X? X will be 5 to the power of what? 4. Right? 5 to the power of 4. So you apply definition. You apply definition. Any questions so far? Any questions so far? 5 to the power of 4, you can multiply, which is 25 times 25, 625. Or you can just leave it like that. You can just leave it like that. Okay, leave it like that is fine. Okay. Now, are we ready for more? Of course you are. Of course you are. Okay. So let's look at number 2. How about number 2? Log base 2 of 16 is equals to X. So what does X equal to? What does X equal to? It looks a little different, right? It looks a little different from the other 2 equations we had. Well, you just have to simplify this whole thing. Okay, this really just tells you X equals to what? X equals to what? You just switch sides, same thing, right? So log base 2 of 16, and 16 is 2 to the power of 4. So the answer is 4. Are we good? Are we good? Is that pretty easy? Okay. How about number 4? Can you guys do number 4? Okay, I'm going to give you a couple of questions, okay, because it gets a little easier and I want to make sure you guys are practicing. Okay, so you guys are going to do number 4. Number 4 is a common log 0.1 equals to x. And I also want you guys to try number 5. Okay, so 4, 5, 6. You can use definition. It's just a miscellaneous of questions here, right? And number 5 is log base 3. Oops, sorry. Log base 3 of 81 equals to x, right? 6. It's a log x. You can see that log depends on where x, depends on the position of x, right? Depends on the position of x. Number 6. Depends on the position of x. You see, in this definition we have learned here, there's 3 positions. Okay, the position at the base, the position at omega, and the position on the other side. Okay, all these relative positions must be honored for their value, Okay, 3 positions, 1, 2, 3. Okay, so 1, 2, 3. And all of these are corresponding to each other. They're exactly matching perfectly. They matches perfectly. Okay, in number 4, you can see the base is 10. Base is 10. Omega is known, and the triangle is unknown. And in number 6, omega is unknown, base and the triangle are known. So you have to recognize those different positions. You have to recognize those different positions, okay? So now I'm going to solicit answers from you. I'm going to solicit answers from you. So number 4. What is the answer for number 4? What is the answer for number 4? What is the answer for number 5? And what is the answer for number 6? Your turn. Marcelo, what do you think the answer for number 4? Francisco, what do you think the answer for number 5? Alan, what do you think the answer for number 6? So put your answer on chat. Put your answer on chat. No pressure of any sort, but I do want you guys to participate actively. You can see any one of the 3 positions. There could be a variable there. There could be a variable there, right? There could be a variable there. What is x for number 4? Well, in this case, x is just log base 10, common log, right? And 0.1 is really what? It's really 1 over 10, isn't it? 1 over 10 is 10 to the power negative 1. Therefore, this equals to negative 1, right? Next one, log base 3. So you have to understand the position because every position has their place value, 81 is 3 to the power 4. And therefore the answer is 4 because 3 to the power 4 is 3 to the power 4. We're applying the definition all the time. Okay, x here, x is in the position of the omega. We know the base is 3 and we know triangle is 3. Therefore, x equals to, x is the omega. So x equals to 3 to the power of 3. 3 to the power 3, of course, 27. Right, so that's this group of exercise, this group of exercise. Let's do some more. Let's do some more. Okay, we're gonna carry this with us. We're gonna carry this with us. Let's look at the next group. Okay, let's look at the next group. And this time, I'm gonna assign some questions to you guys. Okay, I'm gonna assign some questions to you guys. Number 7, 8, 9, 10. 7, 8, 9, 10. 7, 8, 9, 10. 4 questions. Okay, we have 4 questions. 4 questions. 7, 8, 9, 10. 7, we have a log base 4 of 2 equals to x. Okay. Number 8, log base 4 of x equals to 2. Number 9, log x equals 2. This is a common log. Number 10, log base 5 x equals to 2. So you can see by the definition, right? All of these quantity, all these variables show up at different places. So just because it's called by that name, it doesn't mean that they don't acquire the same place value. Okay, so quantities at different places, they acquire different place value. Okay. So now, what does x equal to here? It gets a little bit harder, right? Well, if you see, right, this is a 4. There are multiple ways you can do this. There are multiple ways we can do this. If you compare with the definition, this is a 4, base is 4 now, right? Omega now is 2. So this omega is 2. The number at the place of the triangle, that's x, right? So we can remove that. 4 and 2 has a relationship, isn't it? 4 is 2 squared. 2 squared. Oh, this is x. I'm sorry, I forgot to change that. Okay, 2 to the power of 2 and then x. So this will lead us to what? So on the next step, right? And this will become what? 2 to the power of 2x. You're gonna multiply these two exponents. So 2x, and that equals to 2. 2 is the same as 2 to the power of 1. So now they have the same base 2. So 2x equals to 1. 2x equals to 1. So as a result, x equals what? X equals to half. That's just one way to do it. That's just one way to do it. Okay. Do we have I just said, there's another way to do it. Another way you may like it, you may like better. Okay, another way to do it, you might like it better, is that you can go straight from here. Okay, so I'm gonna switch sides on these two. Okay, I'm switching sides. Okay, and log base 4, the base is 4. The base is 4, but 2 is equal to square root of 4, isn't it? Right? And log base 4 of root 4 can also be written as a 4 raised to the power of half. And therefore, it is equals to half. So there are 2 different ways we can do this. There are 2 different ways we can do this. One way is you transform it to the exponential form in the by definition. And the other way is you just deal with it directly. You just deal with it directly. Okay, so you guys want to try another one? All right, so I'm going to give you some time to try 8, 9, and 10. Okay, be careful about their place value. Okay, be careful about their place value. Eight, 9, 10. Oh, the 10 is hiding. Okay, 8, 9, 10. I'm going to give you 4 minutes. 4 minutes. Work on number 8, 9, 10. No pressure. Okay, do the best you can. I'm just going to grab a little something to drink. I'll be right back. Oh, where's my teacup? I'll be right back. Okay. Oh, I'm sorry. I just keep myself on the mute. So what I said, I didn't hear. You didn't hear. I will repeat it. Okay. What is the answer to number 8? Alan, do you have an answer to that? I was doing all the talk and I forgot to. 2 squared. But our base is 4. Did I copy the question right? Yeah, my base is, our base is 4. Are you sure you get 2 squared? You see, log base 4x, the base is 4. The base is 4. The quantity at omega position is x. So this is x. The quantity at the triangle position is 2. So this is 2. And that is 2. So x equals what? That's right. That's right, Alan. It's 4 squared, which is 16. Right? Now, of course, you can check your work. Of course, you can check your work. Right? If you check your work and you plug in, right, your x is 4 squared. And that's going to be equal to 2, equals to the right-hand side, right? Now, 9 and 10. 9 and 10. What does x equal to? Francisco? Marcelo? Marcelo. Okay, apply the definition. Okay, do the application of the, do apply the definition, which is right next to you. Have scratch paper with you. You see, if you look at the definition, there's 3 positions. On these 3 positions, it really doesn't matter what number is, what symbol you use. Is there a place, the 3 places, they each have their value. They each have their value. That's the base, and that's the omega. What is omega? Omega is base to the power of triangle. So triangle has its own position. It acts as a power. So this triangle power, the B equals to omega, right? The triangle power, the B give you omega. So that's how they're locked in the relationship. So now number 9, what do you get? X is in the position of omega, isn't it? And what is the base? Base by default is 10 because we write it that symbol. That's imply the base is 10. So here, this base is 10. Base is 10. Okay, I'm waiting for you guys to finish the rest. The base is 10. When base is 10, by default. So now, Francisco, can you tell me what x is equal to? Can you tell me what x is equal to? Marcelo, what do you think x is equal to? Marcelo, what does x equal to? Ellen? Okay, still thinking. 10 squared, that's right, 10 squared. 10 squared, right? See, omega is what we want to know. Omega is the base to the power of triangle. Triangle is in this place, so that's a 2, right? That's a 2. And so this is omega equals 10, that's a 100. Okay, that's 100. Now, positioning, right? If you look at number 10, the base is 5, so all the bases turn to 5. 5. Right, we don't need that. Turn to 5. Omega, it's like a matching game, isn't it? Is it like a matching? Right? Omega is in the, x is in the place of omega. So this is x. Okay, and x is in place of omega. Triangle, the place of triangle is 2. Therefore, this is 2. And now x equals to 5 squared. You see that? So x equals to 5 squared. And that's 25. Okay, now let's look at the next group of exercises. Okay, let's look at the next group. The next group, you can see the unknown, the variable is at the position of the base. Is at the position of the base. Okay, so we're gonna start working on 11 and 12. 11 and 12. Our tool is still the definition. Our tool is still the definition. So I'm gonna bring the definition to the top. Let's look at 11 and 12. 11, 12. Okay. So what is it 11? 11, the base is x. Okay. Omega place is 1000. And the triangle is 3. Okay. So if you look at the definition, so now what place do we have the unknown? The unknown is at the position of the base. Number 12. Log base x. And the number at the omega place is 25, and the triangle place is 2. Do you follow me? Okay. It's still the same definition. Be aware that the base we're looking for must be positive and not equal to 0. So you're gonna identify the x, but this x cannot be negative. It cannot be 0. It has to be larger than 0 and not equals to 1. Okay, so that's the kind of base we're looking for. Now, the base is unknown. Base is unknown. Base is x. The quantity at the omega position is 1000. So omega place 1000. Triangle is 3. Triangle is 3. So this triangle is 3. So this guy is 3. So that is a 3. So from, if this is true, right? If this is true, then we got this. We get x to the power 3 equals to 1000. If x raised to the power 3 is 1000, what will be x? What number raised to third power equals 1000? 10, right? Is that 10? 10 to the power 3 is 1,000, right? 10 to, but you can also take a cubic root on both sides if you want. Okay, but in any case, in this case, you just x equals to 10. So on this definition, your unknown could show up at the base, your unknown could show up at the omega, your unknown could show up here. Anywhere it could be the x. But a different position of the x, its place value is different. The place value is different. So I want you guys to try number 12. I'm not gonna watch you, so please try number 12. Okay, similar. Okay, take your time. Identify the base, identify the omega, identify the triangle, and on both sides to see what you get. And the base we're getting has to be larger than 0, not equals to 1. Okay, 2 minutes. No pressure whatsoever, okay? You try the best you can. If you want to submit, you may. You're greatly welcome to submit. 2 minutes. How's it going? So the position of the base is x to be found, right? And the position of omega, we know that's 25. 25. And the position of triangle, we know that's a 2. So there's 2. So x squared equals to 25. Yay. We're getting closer to the answer. We're getting closer to the answer. So from the left hand, so from what's given, we get x squared equals to 25. If x squared equals 25, what does x equal to? Well, you can take square root on both sides. When we take square root on the left-hand side, we take square root on the right-hand side, the square root of 25 is a 5. And the square root of x squared is going to be the absolute value of x. And solving this absolute value equation, x will equal to what? +5 or -5. Okay, but remember our base has to be larger than 0, not equals to 1. Therefore, -5, then you say -5 is not fitting to be the base, to be a base of a logarithm function. WNCT, thus x equals to +5. X equals to +5. Got it? Is that good? Are we good? All right. So we have 4 more in this section. 4 more in this section. 13, 14, 15, 16. Okay. Are we ready? All right. Let's do it. Let's do it. Okay. Of course, we still have the definition. I'm still going to carry the definition. All these exercises is to help us to use definition well, Okay, so number 13. 13, 14, 15, 16. Okay, you guys get to be involved, okay? 13 is log base x. So all of these questions has log base x. So to be found, the base is to be found, right? And the next one is log base x of 8 equals to 3/2. Number 15, log base x of 6 equals to 1/2. Last but not least, of 3 equals to 1/3. Okay, so let's see how we solve these equations. Okay, so I'm gonna show you one more example, and then it's your turn. Okay. Once again, you can see x is in the place of base. So this is going to be x. Okay. And we need to be reminded the base has to be positive, not equals to 1, right? And omega, at the place of omega is 16. At the place of triangle, that's 4. Got it? Omega's place is 16. And the triangle place is 4. There. So we end up with x raised to the power 4 is equals to 16. Okay. And then you're going to take a 4th root. You're going to take the 4th root on both sides. The 4th root. The 4th root of 16 is 2 because 2 to the power 4 is 16, right? And how about on this side? This side, because it's an even number root. So it's the absolute value of x equals to 2 and x equals to what? X equals to +2 or -2. But as a base, x base cannot be negative. okay? -2 is not fitting to be a base, for a logarithm. Thus, x must be equals to +2. Okay, so that's the same narrative. Okay, so here, what we used here, very similar to square root. Okay, so here I want to give you the summary. We all know that when we have square root of x squared, okay, square root of x squared, and that is equals to absolute value of x. Okay. Cubic root of x to the power 3, it just equals to x. Now, how about the fourth root? The fourth root of x to the power 4 is going to be absolute value of x. So did you find a pattern? Fifth root of x raised to the power 5 is going to be x. So the list go on forever. You can see if we have even number roots. Okay, √2, power 2. √4, power 4. √6, power 6. You always get absolute value of x. For cubic root, however, √3, power 3. It's the same as x. √5, power 5, it's equal to x. Is that clear? So now please try your turn, okay? Your turn. You're gonna try number 14, 15, 16. Okay, I'm gonna give you until 11:30, until 11:30. Okay, and after that we go over them and then take a break. Okay, go ahead, you can do it. I trust you can do it. I'm sure you can do it. Okay, do it one at a time. Use definition. Use definition step by step. Use the definition step by step. You can do it. Okay, come on, let's do it. Keep going. How's it going? So we have x here. X is the base, right? X is the base. Omega, that's 8, right? Base is x, we don't know. Omega is 8, right? Triangle is 2 under 3. And triangle is 2 under 3. Right? So it's x raised to the power. So from this step, it tells us x is powered by 3/2 equals to 8. So that's what we got. So that's the next step using definition. And then what do we do? What is this? This is actually, if you rewrite it, right? If you rewrite it, it's x raised to the power of 1/2 and then raised to the power of 3. Okay, because 3 times 1/2 is x raised to the power of 3/2 equals to 8. So what this tells us is that this is really square root of x. This is really just square root of x. Okay, so this is a square root of x. Okay, so the square root of x equals to 8. Okay, the square root of x equals to 8. Now we're trying to find out what x is, right? So first of all, we can take a cubic root on both sides. We can take a cubic root on both sides. Cubic root. The cubic root of 8 is a 2, right? Because 2 raised to the power of 3 is 8. So as a result, on the left-hand side, you just have the parentheses left. Right? You have a root square root of x here. That's equals to 2. And then if you square both sides, if we square both sides, what do we get? If we square both sides, x equals to 4. Okay, so here we're touching to something like this. That is equals to x, okay? But x squared inside, the square is outside the root and the square is inside the root. Are they the same? The answer is no. They're not the same for even number roots. They're not the same for even number roots. Okay, so instead of having you memorize these, I'm going to explain a little bit more about this. Okay, so you can see the question gets a bit more complicated, right? So now, I'm going to put it as a note. Okay, explaining this. Okay, and what is more, I'm going to put it as a full page. Okay, so please take notes and really listen to this. We all understand this guy, right? Why we have such a difference? Why we have such difference? Right? The answer is why. You have a square root of x, and then you square it, versus that you square it and then take a square root. What's the difference? From functions perspective, from the order of operations perspective, right? On this piece, the order of operation, and on this other piece, the order of operations are different. Okay, order of operations. Okay, so on this piece, they both take the same input x. Okay, x is given to the input. But the first operation will be done is the square root of x. Okay, after square root of x is done, and we're going to square it. That's the order of operation. On the next one, however, okay, x is going to be given as input. We're going to square it first. And after we square it, and then we take a root. You see the difference in order of operation? This difference in order of operation makes a big difference, Because of this, on this step, right, in order to make sure we can take square root of x and still stay in real number, we have to require x is greater than or equals to 0. Okay, so that caused the domain. Okay, that caused the domain to be x is greater than 0. Okay, because when you take a square root, you have to make sure you take square root of a non-negative number. If you take a square root of a negative number, you get to the complex number, and we're not dealing with a complex number here, right? So that the domain is different. On this piece, right, before we take a square root, we already square the input, and the domain here is all real numbers, negative, positive, 0. They're all fine. Because after you square each number, you square a positive number, you're gonna get positive. You square 0, you're gonna get 0. If you square a negative number, you're still gonna get a positive number. So these two operations are different. And that difference makes a big difference. That difference makes a big difference. All right. So that's why that in here, when we square both sides, okay, one equals to x, and the other one has to be equals to absolute value of x. Okay. It's a tough stuff. You know, a lot of people get really, really confused. Okay. Trust me, a lot of you may get confused as well in the future. But if you remember the order of operation, just go back to the basics, you will be able to figure out yourself. You'll be able to figure out yourself. Okay. Any questions so far about the steps? Number 14, you can see, obviously, it takes multiple steps, right? It takes multiple steps. Do you have any questions? We'll come back to do 15 and 16, and then we're going to summarize. You should expect another quiz this week, as I said earlier, but I think I muted myself, so you probably didn't hear. Okay, and after the break, I'm going to go over our plan for this week and next week and the last week. Wait, this week is week 14. Yeah, we have 2 more weeks to go. Okay. All right, so let's take a break for 10 minutes. When we come back, I will take your questions. Okay, we're back at 11:47 a.m. All right. So I will see you guys. Let's see. Do you have any questions on what we have done so far? Do you guys have any questions on what we have done so far? No? Okay. So if you don't have any questions, I would like to go back to number 15 and 16. Okay. So let's put these on the top. Okay, let's put these on the top. Okay, so we are to determine the value of x. You can see we have seen a variety of situations, right? So we really need to know how to do them. And now x is equals to what is to be discovered, right? It's to be discovered. So we will apply the definition, right? We keep this in mind, right? You keep this in mind, that's what we want. And the base is what is to be found. Base must be positive and not equals to 1. And the number at a position of omega is 6. So this is 6. Triangle, the quantity at the place of triangle is half. Half. So this quantity is half. Triangle, right? And base, of course, is x. So from this, from what's given, right? If this is true, then we apply definition, and we ended up with something like this: x raised to the power half equals to what? Equals to 6. And x raised to the power half is really square root of x. Square root of x. So square root of x equals to 6. If we square both sides, x must equal to what? X must be equals to 36. You follow me? When we square both sides, when we square both sides. When we square both sides. Right, this is one of the basic, you know, we did this similar things way before midterm, right? The 3 types of equations, remember? Okay, 3 types of equations. I think it's back in basic 11 or 12 or something like that. Okay, and x is 36. So the base is 36. Base is 36. You can always check your answer. You really can check the answer, right? I'm going to check the answer. How do I check the answer? When I check the answer, I go back to the one side of the given equation. So that's the left-hand side, right? And I got my x equals 36. 36. And then does this equals to half, right? And then you figured, okay, 6 equals to the square root of 36, right? And that is equals to log base of 36, and square root of 36 is 36 raised to the power of half. And therefore the answer is going to be half. Right? So left-hand side equals to right-hand side. We got the right answer. We got the answer. Number 16. Okay, number 16. This time the scenario is, you know, the B is to be found, right? Because at the position of the base, it's x. So this is x, so that's x. At the place of omega, that's a 3. So this is 3, and that is a 3. Triangle is 1/3, right? 1/3. So triangle, at the place of triangle, that's 1/3. So there you go. We got x raised to the power 1/3 equals to 3. What do we do? X raised to the power 1/3, that is cubic root of x. That's equals to 3. Then what can we do? We're going to take a third power. We're going to power both sides by 3, okay, to isolate x. So we're going to power both sides by 3. Power both sides by 3. And the left-hand side is x. And the right-hand side, of course, is 3 to the power 3. 3 to the power 3 is 27. Okay, so that's the power, you know, that's the situation. So let's check our answer. Let's check our answer, right? We have the left-hand side. We have the left-hand side. Right, left equals true. That's the left-hand side. X is 27, right? X is 27. So log base 27 and 3 is 27 power by taken third root. 1/3. And therefore the answer is 1/3 indeed. Okay, so we found the solution. The solution indeed is 27. It's 27. Any questions so far? So these equations actually a little bit challenging, isn't it? Isn't it? Is it a little bit challenging? Yes, it's a little bit challenging. But if you use definition, you can transform from logarithm to exponential, exponential to logarithm interchangeably, so that then you can tackle, you can finish, you can solve the problem. If this is difficult for you, I would encourage you to watch the recording again, because at that time you can play back, you can watch it over, you can pause, and if you have any questions, then please write it down and bring them to me. Bring the questions to me, okay? All right, very good job, very good job. You have followed me up to this point, okay? You follow me up to this point. Now, the next section we want to get to, if you need more exercise, there's an alpha 60B, and today we want to get to alpha 61A, 61A. Okay, we're gonna see how alpha 61A works. Okay, are you guys ready? And of course, you're given the formula at the beginning, but just ignore the formula, because those formula is not, well, they're true, but we have to understand it. We're gonna, you know, I'm gonna show you certain things for you to truly understand and not making those common mistakes. Are you guys ready? And sit tight. And sit tight. Okay, sit tight. First of all, I would like you to have your paper pencil with you. Paper pencil with you. Paper pencil with you, please. I'm going to give you a couple of questions. For example, if you have log base, say just base log base 2, and you're given that one number plus another number, is this correct? Is this correct? For the same issue, if it's subtraction, would that be right? Are these right? Would you like to volunteer your answer? Then you say, what is A, what is B? A and B, just arbitrary number that are fitting to be in their place, to be in that place. Are these correct? So if someone show you that word, right? Do you agree with me? Do you agree with them or you don't agree with them? Because you're gonna start to grow a little suspicious, right? She's asking if that's correct or not. Do they look right to you? 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 Can you give me an answer, or you don't? Or are you going to withhold your answer? You don't want me to know. How about we do this? Okay, you're going to do this to yourself. I'm not going to solicit your answer. I don't need to know. Okay, you're going to say, okay, these two. If these two look right to you, you're going to write it on your piece of paper. For yourself, if you don't want anybody to see, nobody has to see it. Okay, you write it down, you agree with it or you don't agree with it. 1 second. Is that enough time? So it's entirely yours, okay? You have no obligation to report to me and I'm not gonna judge you. Okay, at least you're not gonna feel judged because I'm about to tell you the answer. I'm about to tell you the answer. Okay. Are you ready? Did you write down that secret answer that nobody else need to know? Just yourself. Did you write them down? Did you write them down, Ellen? Marcelo, did you write them down? Did you write them down? Yes. Okay. So I don't need to know the answer. Okay, you don't need to tell me. I'm going to tell you if they're right or wrong. They are completely wrong. It looks very intuitive, isn't it? It looks very intuitive. Okay. In fact, similar mistakes could show up in different shape and forms. It could be common log a plus b equals to log a plus log b. Okay, common log a minus b equals to that. And they are completely wrong as well, even though they look very intuitive. And what is more, I want you guys to write these down so you not make these mistakes. Even Ellen, in the future, you're going to encounter Ellen. Okay, you're going to encounter Ellen. Okay, write these down and make sure they're in front of you and you mark them as incorrect. You follow me? They look very intuitive and it feels right for a lot of our students. You're not alone. If you mark the answer yes, you're not alone. I would say 90% of the student may come up with these answers. Okay, I wish you were the 10%, right? I don't know. My estimate is purely, just my estimate. Okay, my guess, because these mistakes, okay, are so prevalent. They're so prevalent. They are just completely wrong. Completely wrong. Okay, have a good laugh. Have a good laugh. Completely wrong. But yet, you can see how easy to make these mistakes. Do you see that? It's very easy to make these mistakes, don't we? Now the question is why they're wrong. Why they're wrong, right? So I'm going to show you why they're wrong. Okay, so could you please write them down? And these are completely wrong. I may as well give you some other forms. Okay, for example, I can continue to give you these forms. Okay, these forms will include even more general form. Log base b, capital A plus b equals to log base b, capital A plus log base b. And these are very, very common mistakes. Okay, this is a minus. You can see they're all the same category of mistake. Okay, and we see them in different sizes and different shapes and sizes, and they're all, now I'm, in order to emphasize, they are terribly wrong. Extremely bad mistakes. All of these. So write them down on your notebook, maybe put it in on one page, on one entire page. Okay, write this down one by one. And then after you write them all down, because I tell you they're wrong, you don't have to believe me. Unless you're convinced, right? Because if you're not convinced they're not right, you're gonna continue to do that. You're gonna continue to do that. And these are the mistakes we see not only at intermediate algebra class. We see these mistakes in college algebra. We see these mistakes in pre-calculus. We see these mistakes throughout the calculus classes. That's how serious these mistakes are. Okay, that's why I want to I want to start with addressing these mistakes. Okay, and the mistakes people show, okay, people will see these mistakes or continue. So since you have that page, let's get that page filled, right? Some student in the calculus class, they see 1 plus x, and they will say, hey, that's equals to ln 1 plus ln x. And you can see that's another version of this mistake, isn't it? Right? You see that? That's the other version of this mistake. So this mistake really show up in many different faces, right? They show up in many, many different faces, in different shapes and forms, but they all originated from the same misconception. And the letters may not be, for example, another situation could be, and I cannot, excuse me, I cannot enumerate them more, but I do want to give you the mistakes I have seen over the years, okay? Which is log 1 plus log x squared. Okay, many, many more. There are many, many more, okay? Does that fill your page? Do all of these fill your page? Okay, so I want you to reserve this page for yourself, cross them out, okay? And you tell yourself, okay, I'm sure when you tell yourself these are mistakes, you may not be quite convinced, because the next thing I will do, I will be trying to convince you. Okay, I will be convincing you. I will tell you why they're mistakes. Okay, so all of these are terrible, horrible mistakes. and yet they are very popular. They're very popular. In your future classes, you might see your classmates making these mistakes, but you're not going to. You're not going to. That's what I hope for. That's what I hope for. Okay. In the future, say 2 years down the road, you're taking a calculus class, you might see your classmates is making these mistakes, but you are not going to make that mistake. Okay, so that's what I'm hoping for, okay, through these discussions. So anyway, without further ado, okay, I'm going to explain to you why these are mistakes. Okay, so I'm going to take one simple case to give you a counterexample, because mathematical truth is what? If true, always true. If false once, it's false. So I need to give you that false once situation, don't I? I need to give you that false once situation. So that situation I'm going to pick is going to be this one. Okay. Okay, I'm going to give you a counterexample for that situation. Because if this counterexample is true, if this counterexample counter them all, counter this, it counters all. Okay, if it counters this case, it counters all. Okay, so I'm going to give you a counterexample. And I'm hoping that from this counterexample, you are going to be able to get many more. You're going to be able to get many, many more for us. Okay, so I'm going to give one counterexample. And in this case, I'm going to give you A equals to 2, B equals to 4. Okay, B equals to 4. So from the right-hand side, okay, so from the right-hand side, I start from the easy part. I start from easy, right? A is 2, B is 4. What does the log base 2 of 2 equal to? That's equals to 1, right? What's the log base 2 of 4 equals to? That's equals to 2. So the right-hand side equals what? It equals to 3. Okay, so how about the left-hand side? How about the left-hand side? The left-hand side, okay, I'm going to have 2 plus 4. And that, by order of operation, I will have a log base 2 of 6. Are these two equal? We know that 3 is equals to log base 2 of 8. Right? We just did that, right? We did numerous examples. Are these two the same? They're not the same. They're not the same. Okay? Log base 2 of 8 is not the same as log base 2 of 6. They're not the same. Thus, this statement is false. If that statement is false, that's just one case of base 2. And if I change to base B, base any base, right? If I change it to any base, that is also false, right? Because base 2 is one case of any base. Okay, so i.e., for any base, that is false. So are you convinced? Are you convinced by me? And for subtraction, you can do similar things. You can totally do similar things. Okay, so I'm going to give you some time to work out the subtraction case. The subtraction is not true either. Do you guys hear the logic? False once, false. Okay, so this statement, okay, this statement is a false once. False once in the case of A equals 2, B equals to 4, it's been false. A false once, false. Okay, this is why this is false. If this is a false as a special case for base 2, and it is for any case, it's false, because any case include base 2 case. So if base 2 case is false, the entire thing is false. You follow me? So now I want you guys to work out a counterexample. Okay, so please give a counterexample for subtraction. Your turn. You give a counterexample. You don't have to be restricted to what I have done. Okay, you can be totally creative. You can be totally creative. You have to make sure A minus B is also positive. Okay, you don't want to deal with a negative case, and that because that will be undefined. Okay, we will consider all of these in the domain of logarithm. So we're not gonna even consider the cases that the logarithm is undefined. If undefined, there's no comparison. Okay, we don't consider these cases, even within the well-defined function, and that is false. So we want to give such an counterexample. Okay, I'm gonna give you a couple minutes. Okay, I'm gonna give you a couple minutes. Go for it. You have many examples. Okay, you don't have to use my example. You can use any other people's example. Get it? Can anybody contribute to your counterexample for that? Because we must study this so thoroughly so we never ever make that mistake. Given that these mistakes are so popular, they're rampant. They're rampant. They're like a pest. Okay, these pests scattered into your work of mathematics, and you lose points here and there. You lose points all over the places. You don't want that to happen. You don't want that to happen. Okay, so your teacher just take 2 points here, take 2 points off here, takes 3 points there over there. How can you afford something like that if you want to do well on your exams, right? On your coursework. No, we don't want that to happen. So we have to understand these mistakes thoroughly. Okay, so every time you see that, you have the instinction to do it, then you realize, wait a minute, I have that counterexample. I cannot do this because false ones, false, right? If it's false ones, it is false, right? So you always will need to remind yourself. So now, what is the counterexample? Anybody want to contribute? Alan, Marcelo, any one of you like to contribute to a counterexample, counter this other case? Counter this other case. You ready? Counter the other case. Ellen, are you ready? Marcelo, do you have a counterexample for them, for this latter statement? What A you will set up to be, and what B you're going to set up to be, and you're going to make the case that it is a false statement. Ellen, do you have one? No, not yet. Okay, how about I give you one? A equals to 4, B equals to 2. Is that simple enough? Right? You have many more. Okay, so and look at the right and look at the left. Okay, we look at the left and we look at the right. The right side, left-hand side. Okay, left-hand side, right-hand side. So A is 4, B is 2, right? And what does that equal to? That's log base 2 of 2, right? 4 minus 2 is 2, that equals to 1. And this one, right? This is a 4, and this is 2. So that's going to be 2 minus 1. And they're equal. Oh my God. This is not a, this show that it's correct. Can we say it's correct? The answer is no. You only show one supporting evidence. It is true. There are cases it's not true. So you have to keep looking. We have to keep looking until we search through, or we can, well, ideally we'll mathematically prove it. So obviously this example doesn't prove it's wrong. So how about I choose 8? I want to choose 8. I'm choose 8. Right? So now this time it's a 6. And that's not equal to 1. Right? Just keep looking, keep playing with those numbers. Some number may support it. Some number do not support it. You follow me? But if it's false once, it's a false. False one. You only just have to find that a case that's false. I already told you it's false. So you must be able to find a case that's false. Are there situations you never be able to find a mistake? Yes, that's how mathematics is discovered. Sometimes you keep trying to find counterexample, but you look high, you look low, you look left, you look right, don't find one. Then you think maybe it is true. Maybe I can prove it is true. If a mathematician can eventually prove something that is true rigorously in mathematics, and then it will be a true. It will be a true. Okay, but until it's proved true, okay, we keep looking for counterexamples. We keep looking for the counterexamples. But anyway, without further ado, so this time this is 3, and that's -1, that's a 2. Right, 3 minus 1 is 2. Are these two the same? Of course not. Log 2 is equals to log base 2 of 4. You see, we found one. We found the first one didn't work and we throw it away because we need a counterexample. We want an example that counters it. We don't need to demonstrate every example counters it. We only need one counterexample because the mathematical truth is judged very rigorously. If true, it has to be always true. False once, we don't need it false twice. Okay, false once, it's false. You follow me? Therefore, we found it. So log base 2 of 6 is not the same as log base 2 of 4. Okay, and that's the ones, false ones. Then we can say thus, this is what is false. If that is a false, okay? And that for any base, right, including common log, base 10, for any base, it is false. You see how, you see the power of this counterexample. This counterexample is very powerful. I want you guys to create your own counterexamples and work through your fingers. So that way you will not make those mistakes, right? You're not making this mistake. That's what I hope. I hope, because these mistakes I've seen at, as I said to you, at all levels, from intermediate algebra when we teach the beginning of the logarithm until all the way up to calculus classes. The student may just make these mistakes. Isn't that frustrating? It's frustrating for both the teachers and the students, in particular for the students, because they are the ones who have to bear the consequence of these mistakes. Okay, so now we have told you what is wrong, what cannot be done, but what can be done. What can be done, right? What can be done. Okay, which we go back to the beginning. We go back to the beginning of alpha 61A. Alpha 61A. You know, you see at the beginning of that, you have 3 formula, right? So what is true? What is true? Okay. So I want to derive this with you, and I want you to have the paper pencil with you, because I believe that if you derive it yourself, okay, you first watch me deriving it, and then you're going to derive it yourself at your private time. Please do it. Please do it, because this will guarantee, like a double guarantee, that you'll not make those other mistakes, which cause you lose points here and there, everywhere. Okay, so the first one, I want to start with something we're very familiar with. Okay, we know that b to the power m multiply b raised to the power n equals what? B raised to the power of m plus n. Do we agree with that? Yes or no? Yes? Okay, so we agree with that. Now, this is true for any base. In particular, if we restrict the base to be positive, not equals to 1, and they're still true, right? So these are still true. So in these cases, is it also true, right? Because if these are true for any base, of course it's true for any This is for any base b. So now if we have a restriction on the base, of course it's still true, right? It's still true. So in the following calculation, we're going to be using, so in the circumstances, okay, we have that situation. And we know that this is true. This is true. Right? We know that's true. So we're going to start from here. All right? And we're going to combine that with our definition. Where is our definition? Our definition we have used for so long. I'm just going to copy and paste it here. So you have a sense that we have been doing this, right? We've been doing this. Okay, I'm going to show you how these are being derived, how the new formula being derived. Okay, for b to the power of m plus n, for b to the power m, we know these two are equal, right? We know these two are equal. b to the power of m plus n, in this situation, okay, so I'm going to make 3 cases. Okay, I'm going to make 3 cases. On each one of the cases, I'm going to apply b to the power m. I'm going to, and then I'm going to apply it to b to the power n. I'm going to apply it to b to the power m plus n. So there are 3 cases. You can see they're derived from it. Okay. Since these are on the other side, so I'm going to put it on this side. It doesn't really matter, it's just closer to it. Okay, b to the power n. And I'm going to just put it on this side. M plus n. B to the power of m plus n, right? So now when b to the power m is in place, when this is m, right? This is m. Okay, this is m. So b to the power m is in place. Suppose I call this guy capital A. And I will call this guy capital B. Okay, when b to the power n is in place. Do you guys follow me? Right? So in this process, for example, when b to the power m, I assume that equals to capital A. You see, I'm using definition, don't I? So this is a capital A. A capital A is in the place of omega. Base, still the same. The triangle now is M. Right? The triangle is M. On the b to the power n case, I make it a capital B, but this is a triangle. So this is a triangle N, and omega is a capital B. Right? In the case of b to the power m plus n, right? The triangle is what? It's m plus n. So here, this is going to be m plus n. Omega, what is omega? How about I just call it omega? Okay, I will keep it as omega. I'll keep it as omega. But omega is equals to what? Is b to the power m plus n. Okay, so now what I'm going to do is I'm going to take this piece. You guys see this relationship, right? You're going to see, you saw this relationship. Okay, so in this relationship, I'm going to do a couple of substitution because this tells me omega is b to the power m plus n. Right here. Right? You follow me? Because it's right here. I also know this piece will also lead me to the next one. because b to the power m plus n is equals to b to the power m multiply b to the power n, right? It's right here, right? We know that, didn't we? So we have a relationship like this under the circumstances, okay? Okay, and now b to the power m, b to the power n. What is the b to the power m? B to the power m is a capital A. Okay, b to the power m is a capital A. Do you guys see that? B to the power n is a capital B. You follow me? So this product is right there. And this tells me that log base b of a times b is m plus n. What is m? M is this guy, isn't it? Isn't that right? M is this guy. And n, what is n? N is this guy. That is the first formula in alpha 61A. You can see it's a consequence. It's a consequence of this property we learned in exponential, exponents, under our circumstances, combined with definition of logarithm. Do you guys follow me? And this is called, this is truth. This is truth. Okay, this is the truth. This rule is also has a name. Okay, it's called a product rule. Product rule. It's a little bit counterintuitive, isn't it? Counter the mistakes we have seen before, right? What the mistake we saw? This is false. These are false. And this is true. This is the truth. Okay, provided, of course, A is positive, right? B is positive. Make sure we are in the domain. You follow me? So using this property, okay, using that property combined with definition, we get this product rule. We get this product rule. Got it? Now, let's look at quotient rule. How is a quotient rule derived? How is a quotient rule derived? If we know this is useful in deriving product rule, and now let's look at quotient rule. B to the power m divided by b to the power of n is equals to b raised to the power of m minus n. Who doesn't know that? Everybody knows that, right? And once again, this is true for any base that's not equal to 0. Why do we emphasize not equal to 0? Because if b equals 0, it's going to cause a 0 denominator. So once again, we're going to establish our circumstances. In particular, okay, we are considering the case of 0 is less than b and b is not equals to 1. Right? So not equals to 0. So this is still true. This is still true. Right? Under the special, it's still true. So from here, we're going to work it. We're going to work it. Okay, we're going to work it. But this time, okay, so we're going to set up, all of these are the same. okay? These two are the same, okay? Same thing. So I'm just going to copy and paste, no difference. So you see that the similarity in these proofs. However, I'm going to work this piece, okay? This piece, b to the power of m minus n, I assume that is equals to omega, okay? According to our definition, right? According to our definition, this is going to be log base b omega equals to triangle. And what is my triangle? My triangle, right? You see that this is the by definition, right? But I'm working on b to the power m minus n. So triangle is m minus n. Omega, of course, is omega, right? All right. Does everybody follow me? And b, of course, still satisfy those conditions. Okay. I just want to remind you of that condition. Okay. And also, it's just a very important condition to have. And next, I'm going to single this piece out. I'm single this piece out. From this piece, I know that omega is equals to b raised to the power of m minus n. Right? From here, I also know that I'm going to substitute b to the power m minus n to b to the power m over b to the power m. So over here, I'm going to do another substitution. And this piece will be substituted by its equal, which is this guy. Okay? And b to the power m is what? It's a capital A. B to the power n is a capital B. And what is m? M is log base b of A. And what is n? Lowercase n is this guy. And here we go. We get the second truth. We got the second truth. And this rule is called quotient rule. Remind you of the mistakes we've seen, right? Those subtractions, right? We have a quotient rule. And of course, we need to understand those A must be larger than 0. B is larger than 0, right? Just to make sure everything is in the domain. And B is still greater than 0, not equals to 1. So this is the second rule, quotient rule, product rule, quotient rule. Okay, so I'm going to put it on the top. Product rule, this is a quotient rule. And where's my product rule? My product rule is right here. These are the rules you can use. And of course, there's a third formula, right? There's a third formula. So we have derived product rule, quotient rule, right? Product, the logarithm of product is the sum of the logarithm. The logarithm of a quotient is the difference of a logarithm, of two logarithms. Okay, so that's the narrative. Now, let's look at the third one. Okay, the third one in basic 61A. Okay, let's see what is it. Okay, how is this derived? Okay, do we know this fact? Do we know that? This is true for any base, right? For any base b, right? Yes? Well, except in some cases, you know, we don't want the denominator equal to 0. Those cases, right? And in particular, it is true. Okay, so what is it true? This is true for base, for what? For base 0 is less than b and not equals to 1, of course. So that is true. From it, let's see what we can derive. Okay, so from it, let's see what we can derive. Okay. We have b to the power m, right? So in the definition, all right, b to the power m, we already did something to it, right? We already did something to it right here. So I'm gonna just copy that. So you know, there's similarities. So b to the power m equals to capital A, I assume it. On the other side, by logarithm definition, base b is the same, a is omega, and exponents is m. So they're in place. Okay, so how about b to the power m times n? How about the b to the power m times n? Right, so let me make another box. B to the power m times n. B to the power m times n, and that equals to omega. By definition, what does that lead to? Oops. Right, by definition, what does that lead to? This is a triangle, and this is omega, that's the base. So also on the other side, what do we get? We get log base b omega equals to triangle, right? That's my triangle. Omega is b to the power m times n. Triangle is what? Is m times n, right? And base are the same. You follow me? Now, from here, I'm going to do a couple things. Okay, I'm going to do a couple things. Omega is equals to b to the power m times n. B to the power m times n. Yeah? And b to the power m times n, we know it's equals to what? It equals to what? It equals to b to the power m and then to the power of n. So I'm going to take this guy to replace this guy because they're the same. Yeah? Right? It's just a simple replacement. And then what? B to the power m. What is b to the power m? It's a capital A. So this piece is a capital A. And what is m? What is m? M times n is the same as n times m, right? And what is m? This is n, m, this is m, this is m. So I'm replacing this m by its equal right here. Do you guys see, do you guys follow me? Okay, so in the end, what do we get? We get this third formula in 61A. Then you say, hey, they're not exactly the same because in the formula, it's a capital C. Well, it doesn't matter. I can just give a different name, right? I can just give, it doesn't matter because the power is the same. right? If I put a C and this is C, right? It's C and C. So now this rule is called a power rule. It's called power rule, okay? So this rule is called power rule. And of course, provided we do it in the domain, So this is called power rule. Okay, I encourage you guys to watch this section maybe more times. Okay, so these are the 3 rules of logarithm. These are the 3 rules of logarithm. So let's take a closer look. Okay, so when you have a power situation, right? When you have a power situation, we can bring down the power and keep it that way. You follow me? Bring down the power and keep it that way. Previously, okay, we have learned these facts. Log base b of 1 is equal to 0 no matter what the base, right? And we also have learned log base b of b equals to 1, right? And log base b of b to the power of heart, which we have learned before, and equals to the heart. Equals to the heart. All of these are special cases of this power rule. Okay, so let me draw a picture. Okay, so all of these is being covered. Okay, it covers those previous cases that we have studied. Okay, so these are the special cases of the power rule, and the power rule is this one, it's the ultimate. This is ultimate. Well, this part of the lecture today is pretty intense. I expect you guys, maybe you need to watch it again and again on the deriving. The goal for you is that every one of you can derive this all by yourself. All by yourself. So you no longer have to rely on the memorization. For the remainder of the time, I'm going to show you the application of these 3 rules. Okay, 3 rules. Okay, for example, number 1, right? We have log base 3 of root 27. Square root of 27. What does that equal to? Well, this is the situation we can use the power rule. Excuse me. We can use power rule because square root of 27 is half is the power, right? So we can use the power rule. So we can bring down the half, and then you have log base 3 of 27. And of course, we know that log base 3, 27, that's equals to 3, isn't it? So multiply by 3. And so in the end, the answer is 3/2. Okay, so let's look at the second example. Okay, log base 2 of 160 minus log base 2 of 5. Right? We have 3 rules we have learned here today. 3 rules. I'm going to put it under. Which one? Of course, log base 2/16, you can do it in many different ways. You can use these formulae any way you want, left to right, right to left. Okay, so I'm going to show you one way to do it is using quotient rule. Okay, using quotient rule. And of course, I'm going to show you another way. Base 2. And then quotient rule says if you have subtraction of the same base, and you just simply take 160 divided by 5. What do we get there? So log base 2 of a 160 divided by 5. 160 divided by 5, what do we get? Is that 32? And that the answer is a 5. So you can use a quotient rule. And that's not the only way to do it. That's not the only way to do it. Really, it's not the only way to do it, okay? Or I'm going to show you another way, okay? All of these teaching us to be more flexible instead of being more rigid, okay? Knowing, okay? Knowing 160 is equals to 32 times 5. Guess what? You can also use a product rule. Log base 2 of 32 times 5. And of course, you have a minus another log base 2 of 5. Okay, and using product rule this time, right? Using product rule this time, right here. Product rule. Capital A, capital B, base is 2. So product of 32 times 5, that's equals to log base 2 of 32 plus log base 2 of 5. And we have another subtracting of that. So you can see there are more than one way to do it. These two are identical and they're opposite. Therefore, that makes 0. You don't have to worry about it. So log base 2 of 32 is a 5. So you can get the same answer from different ways. Okay. One more example I wish to go over with you. I know you guys need some practice. I'll leave that for you, and I have assigned you the homework. Okay, number 3. Okay, so feel free to watch the lectures. I think it will become, the recording will be available. And we have such flexibilities, left to right, right to left. Okay, so on number 3, I have this log of 5 plus log 20. You can do it any way you want, okay? But we can apply product rule from right to left, right? You can see log, that becomes 5 times 20. And what does that equal to? Equals to log, right? Log 100. And log 100 equals what? 2. And of course, you can also use product rule. Okay, so we still have a little bit of time left. Okay, so I'm going to show you the other way. You don't have to do every way, but you may like to think about, all these different ways. Okay, all these different ways. Okay, for example, can you do it another way? Log 5. Do you think another way might work? So how are you going to split the 5, 20, right? I want you guys to think about it. Is there another way? Right? So these are all good questions, even though we're done with the question. Is there another way? Using what do we have learned? without using calculator, So I want you guys to think about it. I want you guys to think about it. Okay. And until next time, I will see you guys on Monday. Oh, no class on Monday, actually. No class on Monday. I just realized. No class on Monday. I will give you one more. You have one more quiz. Okay, you have one more quiz. And that one more quiz will, the first quiz I give you this week is due on Monday night. And another quiz will be also given to you on Monday night. Next week, you only have one quiz. That's going to be the last quiz this semester. And then we're getting ready for the final exam. Okay, so regarding the end of semester plan, at the end of the semester. Okay, Monday. Okay, that's 31st, right? No classes. Okay, it's a Memorial Day holiday. And Wednesday, there's a class. Okay, and we're gonna have 2 parts on Wednesday next week. Okay, we're gonna finish up the exercise. Okay, in Alpha 61A, right? We're gonna finish Alpha 61A, and then review for the semester. Monday, okay, which is, I would say it's June. Let's see, what date is that? June. June 7th. Okay, review and final, okay, will be available from June 8th through June what? June 11th. Okay. And then the following Monday, the following week, I like to give myself a little more time and space. The following Monday, okay, grades will be available okay, the week of June. Let me make sure I don't want to give you the, the week of the 14th. The week of 14th. Okay, the week of 14th. It's not guaranteed it's going to be on Monday, but it should be available that week. Okay, so that's the plan for this semester. So these will be on the exam. All of these it's going to be on the exam. Okay, I'm going to wrap it up on Wednesday next week, and you're gonna have one more quiz next week, and that will be the last quiz this semester. Okay, so have a great Memorial Day weekend. Have a great time. Will the final cover everything from the beginning of the class? Yes, the final will cover everything from the beginning of the class, including the materials that's been covered by midterm exam. Okay, and we will have a review session. We'll have review sessions Wednesday next week and the following Monday, as we said on these here. I hope the dates, I think the dates are all correct. Okay, and get started on review. If you have any question, please send them my way, and I will answer them the first moment I see it. Okay, so thank you very much. Have a great weekend. I will see you on Wednesday next week. Bye.